Hi everybody. In today's lecture, I'd like to talk to you about the polarization of dielectric materials. So let's think about what happens when you have that dielectric material in between the capacitor plates. Now remember, dielectrics are insulators. So you can model the molecules that make up the dielectric as dipoles, okay? So now let's remember our dipole moment P is equal to the magnitude of either charge in the dipole Q times the vector L that points in between the two charges. So the magnitude of L is the distance that separates those two charges, and L points from the negative charge to the positive charge, okay? So now let's picture what might happen in a dielectric material before we have any voltage in between the plates of the capacitor. So there's no electric field yet. And in this scenario, you're going to have the molecules, all your little dipoles, and they're going to be randomly oriented. They're going to be all over the place, as is pictured here. Now you apply an external electric field. Okay, what's going to happen? Well, the positive part of the charges are going to want to move downstream on that electric field, right? And the negative part of the charges they're going to want to move upstream on that electric field. But now the net charge, remember these are insulating materials, and so the charge doesn't move well, right? And the net charge on that molecule is still zero. So that means there's no net force to move the molecule right or left here, right? And so what's going to happen instead is that the molecules are just going to then rotate to align with the field. And so you can picture this electric field as creating a torque on your dipole. Now, to go along with the notation in your textbook, we're going to use N here as our symbol for the torque. The vector torque N is the cross product of the dipole moment with the electric field. So here, N is equal to P cross E, okay? And then that's going to cause the dipole moment to align as it shows here. Now, if you picture your dipole moment as pointing from the negative charge to the positive charge, then you can see here E points right and P is pointing at this random angle here, and P is going to want to rotate clockwise to align with that electric field. That's how the torque is going to act on that sucker, okay? Now, you might have wondered before, why, if the electric field inside of our dipole, it would obviously point from the positive to the negative. So why don't we just have the dipole moment vector pointing in the direction that the electric field points, right? Well, this is why. Because the convention is to have your dipole moment such that when you have a torque, that it wants to rotate to align with the field. And so we have to have it pointing from the negative to the positive in order to do that, okay? So what happens is in a real material, of course in a perfect material, all your dipoles would line up beautifully and they'd be straight with the field, ignoring quantum mechanics. But what really happens is that you have this material and there's thermal agitation and there's all kinds of stuff going on. And so the molecules there, they do the best they can to align their dipole moments with the external field. And so they're going to partially align with that field. And in reality, they're going to be wiggling around a little bit, okay? So how much they align with the field actually depends upon the temperature a lot. You know, if it's hotter, they're going to wiggle more and it'll be tougher to align with the field. And it'll also depend upon how strong the field is, right? So in general, the alignment is going to increase with decreasing temperature, right? The colder it is, the less random thermal motion you have, the better the alignment. And also the alignment is going to increase with increasing electric field strength. Okay, now what happens if instead of a molecule, say like water, which has a permanent dipole moment, right? What happens if you have a molecule that doesn't have a permanent dipole moment? What if it's a nonpolar molecule? Well, in that case, what generally happens in a dielectric material is an electric field is applied, and that kind of tugs on the charges within the molecule, right? Displacing them slightly. And so you can see here I have this perfect nonpolar molecule where the negative charge is in the middle and the positive charges are on either side, so no net dipole moment, right? But then in the presence of this electric field, the negative charge gets tugged, and then the positive charge gets tugged left, and the negative charge gets tugged right, and then you got yourself a net dipole moment, right? So when this happens, it's called an induced dipole moment. But then once the dipole moment's there, it acts just like it were a regular dipole. And it turns out that an induced polarization is the effect that predominates in most materials that are used as dielectrics and capacitors. Most of them don't have permanent dipole moments, in other words, or at least not much of one. Now, we can quantify how easy it is to get all this to happen. And so what I mean by all this to happen is, first of all, you've got to induce your dipole moment. And then second of all, you've got to rotate your dipoles to align with the field. And of course, that's going to be a material dependent property, right? Well, it turns out how easy it is to get all that to happen in a material is summed up by a quantity that we call the polarizability, which is often symbolized by a capital P. Now, this is a vector. And the polarizability is the average dipole moment per unit volume in a material that you get when an electric field is present. And since it's a material property, of course, it's going to depend back on that dielectric constant that we talked about in the last lecture, okay? Remember that different materials have different dielectric constants. So our polarizability, we can say, is P is equal to epsilon naught, our permittivity of free space, times that electric field, E, times kappa minus 1, where kappa is our dielectric constant. Okay, so that's how it's all summed up. And you can see here that it's a material property here. The dielectric constant would actually change slightly depending on the temperature. And then the electric field strength, that's already in the equation. So you can see that the polarizability would then depend explicitly on the electric field strength and then kind of implicitly on kappa. Okay, so in reality, what happens at the atomic level with the electric field and material is really very complicated. I mean, if you picture yourself, zooming down to Ant-Man size, then you can envision this nucleus at the center, and then these electrons whizzing around, and then you've got your neighboring atoms with their own nuclei and electron clouds. And so you can imagine that if you were walking around there on the scale of, say, sub-nanometer, then the electric field might vary quite a lot spatially, okay? So we're not going to do all that because that would be a hot mess. What we're going to do is we're going to think about what happens on average, okay? And on average, this little picture, this little cartoon that we have up here up top is how we model materials, okay? So if you're picturing this cartoon world, okay, you can picture these dipoles trying their best to line up with that external field, right? And then you can see here that at the edges of our dielectric here is this yellow square. At the edges of our dielectric, we have kind of a net charge, don't we? So over here, because of the positive part of our dipole lining up with our right-hand side, we have a net positive charge over there. And then on the left-hand side of our dielectric, we have our negative charges lining up, okay? And so we've got a net negative surface charge on the left-hand side. Well, these surface charges on either side, they actually induce an electric field within the material. Now, because it's positive on the right and negative on the left, the induced electric field is going to point from right to left, right, opposite to the direction of our applied external field, okay? So this kind of acts like a second pair of capacitor plates that produces an induced electric field in the direction opposite to the original electric field. Okay, so let's figure out some math. Okay, we have our pictures in our head. Let's figure out some math. Let's envision this scenario. I'm going to present two scenarios to you in this lecture. Let's do this one first. We've got a capacitor and it doesn't have a dielectric in there. So picture some parallel plates with nothing in between them, okay? This capacitor is then charged by some battery to a charge plus or minus Q naught on the plates. Okay, so it's hooked up to a battery which has a voltage delta phi naught there, and it's charged to its max charge plus minus Q naught on either plate. And then we have our equation for the capacitance for this dielectric less capacitor. C naught is equal to Q naught over delta phi naught. Okay, now you disconnect the battery from your plates, and you do this somehow without discharging it, so there's no discharging going on. So the capacitor remains charged. Then, very carefully, without discharging your capacitor, you insert your dielectric in between the plates, okay? Now, because you've done it so carefully, the charge on the plates must remain fixed, and it's still plus or minus Q naught. But because you inserted your dielectric in there, the capacitance has now gone up. It increases, all right? What happens? Well, that causes the voltage to drop. let me explain. You've got Q naught. If you rearrange your equation for the capacitance, Q naught is equal to C naught times delta phi naught, right? That stays the same. Now, you insert your dielectric. Your capacitance then goes up. It becomes kappa times C naught, right? But your voltage then has to drop because the charge stays the same. What does the voltage become? Well, it's got to drop by a factor of kappa. Otherwise, you wouldn't have Q naught there. So basically, you have C naught times delta phi naught equals kappa times C naught times delta phi, which equals kappa times C naught times delta phi naught over kappa, so the kappas cancel out. So in other words, your voltage must drop by a factor of the dielectric constant, if in this scenario. So we now have our new voltage, delta phi, and that voltage delta phi is equal to delta phi naught over kappa, okay? All right, now, the electric field in between the plates before the capacitor was inserted would be, right, E naught. And E naught would be our voltage, delta phi naught, divided by the distance in between our capacitor plates, D. All right? Now, after the capacitor is inserted, our voltage drops by a factor of kappa. What that means is that our electric field must also drop by a factor of kappa. Our new electric field, E, would be delta phi naught over kappa D, right? And that's going to be our original electric field, E naught over kappa. So we have this result here, that if you have a dielectric inserted in between the plates, that causes a drop of the electric field by a factor of kappa. Now, this was derived for a specific scenario, but it turns out to be generally true. Dielectrics reduce the electric field magnitude by the dielectric constant. Now, the reason this happens is because of that induced field, okay, from our little picture here, right? The polarization of the material causes a surface charge at the faces of your dielectric. And that surface charge creates an induced electric field that's opposite to the direction of the applied electric field, and that causes the electric field magnitude to drop by a factor of the dielectric constant. All right, so now we can get some equations for this induced charge on the surface of our dielectric material. Now remember, we have a bound charge density. Remember that charge densities are just the charge divided by the area, okay? So I'm going to use the symbol sigma for charge density, okay? So that charge density at the dielectric surface is related to the dielectric constant and to the free charge density on the capacitor plates, which is, of course, from that external electric field. Okay, so here we go. We have an electric field that's equal to E naught minus E induced. E naught is the field in between the plates of the capacitor, and the induced field is the field in between the capacitor, or caused by the surface charge. So this is our picture here. The minus sign is because we're taking right as positive and left as negative. Okay, so we have E naught minus E induced. Now, this total electric field E here, we've already said that that's E naught over kappa. Okay, we already said that it was reduced by a factor of kappa. So here we have E naught over kappa is equal to E naught minus E induced. So we can solve for our induced electric field, right? Our induced electric field is E naught minus E naught over kappa. Simplifying, it's E naught times 1 minus 1 over kappa. Now, we have previously discussed what the electric field is in between two surface charges. The electric field in between two equal but opposite surface charges is just the surface charge density sigma divided by epsilon naught. You can look back at some of our lectures on Gauss's law if you want to understand this a little better. So here our electric field from the induced surface charges would be the surface charge density from the surface of the capacitor, which I'm calling sigma induced, divided by epsilon naught. Now that's going to be the electric field due to the capacitor plates, right, which is sigma naught over epsilon naught times 1 minus 1 over kappa. So canceling out the epsilon naughts on either side of the equation, we can see that the surface charge density on the dielectric, right, at the surface of the dielectric, sigma induced, is equal to the surface charge density on the capacitor plates, right, sigma naught, times 1 minus 1 over kappa, right? So we can relate all of those things, the electric field and the surface charge density, and it's going to be proportional there to our dielectric constant. That's going to appear in our equation. Okay, So that was scenario 1. And it was very, very helpful. But now let's picture another scenario, okay? So let's have another capacitor, right? And this one has no dielectric to start off with, okay? And you hook it up to a battery and you charge it. And you charge it until the capacitor plates reach, plus minus Q naught. And you do this with a voltage from the battery of delta V naught. So we have our equation for the capacitor again. C naught is equal to Q naught over delta V naught. All right, but now here's where I switch it up. I'm not going to disconnect the battery. I'm going to leave the battery connected. And now I'm going to slide in a dielectric, okay? So in that scenario, the battery forces the voltage between the capacitor plates to remain the same. And so delta V naught does not change. It remains fixed, okay? So if we rearrange our equation for capacitance to be have delta V naught on the left-hand side, then we have delta V naught is equal to Q naught over C naught before insertion of the dielectric, okay? Now, after insertion of the dielectric, okay, our capacitance jumps up. Instead of C naught, it's now kappa C naught. But in order for delta V naught to stay the same, it can't possibly be the same charge, so I'm going to call that charge Q. So now we have delta V naught is equal to Q over kappa C naught. Well, what must Q be so that delta V naught is fixed? Since delta V naught is equal to Q naught over C naught, that only means the only possibility is that my new charge Q must be kappa times Q naught. And then the kappas on the top and the bottom would cancel out. So what does this all mean? Well, the total voltage between the plates remains the same. The total electric field between the plates has to be the same. But the charge on the plates goes up, right? It becomes kappa Q naught. Now, how does this all happen? How is this working out? Okay. So we've got an electric field in between the capacitor plates that has to be the same even though the charge on the capacitor plate goes up. The only way this is possible is because you have that induced surface charge right next to that plate. And that induced surface charge on the surface of the dielectric is opposite in sign to the charge on the capacitor plate. See here? On the capacitor plate, see here on this left side, I have positive charge on my capacitor plate, which is in orange. But then here in the middle, I've got my dielectric in yellow, and I've got an induced surface charge density at the edge of my dielectric. Well, that induced surface charge density will, of course, be, because of the way that the dipoles rotate, negative. Okay, so we have a negative induced surface charge right here. So if we drew a little Gaussian surface that enclosed both our capacitor plate and the surface of our dielectric, right, then the net charge enclosed by that Gaussian surface is still Q naught, right? So even though the charge on the plate increased, the surface charge density compensates for that, and then I still have Q naught total enclosed by that Gaussian surface, even though Q goes up. Since Q naught total is the same, then that means that the electric field in between the plates can be the same. Okay? So we could write this equation. The new charge on the capacitor plates after the insertion of the dielectric, I'll call that Q, and Q plus Q induced is equal to Q naught. Okay? Now, we already talked about in the equation how Q was equal to kappa times Q naught. That came a couple of slides ago, right, where we were talking about how you had to have the voltage be the same. So Q is equal to kappa Q naught. So now I can solve for Q induced. Q induced is going to be, right, Q naught minus kappa Q naught, or Q naught times 1 minus kappa. Now, remember that kappa is a number that's greater than 1. So that means that the induced charge has to be opposite in sign to whatever's on the capacitor plate. Okay, so that's awesome. Okay, so let's continue on with our little scenario here. Let's say Q induced is equal to Q naught times 1 minus kappa. Well, that's a little confusing to look at, okay, because we know 1 minus kappa is negative, but maybe we forget when we do our algebra, right? So let's just flip that so that it's kappa minus 1 and pull our negative sign out front here where it's really obvious. So we have Q induced is equal to minus Q naught times kappa minus 1. Now it's obvious that it's opposite in sign, right? Now remember that your surface charge density is your charge divided by the area, okay? So here sigma induced is equal to Q induced over A, okay? All right, now remember that the electric field in between two surface charge densities equal but opposite in sign, E induced is equal to sigma induced over epsilon naught, okay? So that means that we have minus sigma naught over epsilon naught times kappa minus 1 being our induced electric field from the dielectric, okay? Now, our total electric field is going to be the sum of the electric field in between the plates of our capacitor, right, plus that induced electric field, the vector sum of those two things. So here we have E plus E induced. Now remember that the electric field between the capacitor plates is caused by that charge plus minus Q, which is on those plates, which is equal to kappa times Q naught. Remember that Q naught was the charge before we inserted the dielectric, and so this is Q is equal to kappa Q naught. It's larger in magnitude, okay? So now our total electric field is going to be, kappa sigma naught over epsilon naught, because our charge went up by a factor of kappa, so that's kappa sigma naught over epsilon naught from our electric field in between the plates of the capacitor minus, right, the induced electric field, which is sigma naught over epsilon naught times kappa minus 1. Now you can see here, with a little bit of algebra, that just cancels out. And E total is now sigma naught over epsilon naught, which is the same as the electric field originally before insertion of that dielectric. Okay? So what does this all mean? Well, yet again, if you look at our total electric field versus the applied electric field, which is between the plates of the capacitor, E total versus E, you can see that the dielectric reduces the net electric field by the dielectric constant. So our total electric field was sigma naught over epsilon naught, and the electric field due to the metal plates of the capacitor was kappa sigma naught over epsilon naught, so that's still lower by that factor of kappa. So that's still true. Dielectrics reduce the net electric field, right, by the factor of the dielectric constant. Now, let's look at that equation one more time. This is the same equation I had on the previous slide. E total is equal to kappa sigma naught over epsilon naught minus sigma naught over epsilon naught times kappa minus 1. Okay, see, I've even highlighted it in yellow here. See this second equation? I highlighted it in yellow, or that second term in the equation, I highlighted it in yellow. That looks awfully like that polarizability equation I showed you earlier, doesn't it? Look here, the polarizability P is epsilon naught times the electric field times kappa minus 1. Well, sigma naught over epsilon naught, that's your electric field, and there's your kappa minus 1. And so all I would have to do is multiply that times epsilon naught, and there I have it, right? So I could write this as my total electric field is equal to the applied electric field minus the polarizability over epsilon naught, okay? This is a fundamental equation that you often see in upper level electricity and magnetism courses. So what does this equation mean? When you have an externally applied electric field in an insulating material, the material becomes polarized. What that means is dipole moments are induced, and then those dipole moments rotate to align with that external field. That creates a net dipole moment per unit volume in the material, the polarizability. This polarization causes an electric field in the material that's opposite to the externally applied field, and that reduces the net field in the material by the dielectric constant. Okay, that's what we got going on. Okay, I know that was a lot to take in. I hope you understood it, and I'll see you in class.